there was an ice dam there that was over 2,000 feet tall, something huge. And when that dam burst, you had massive floodwaters that moved, car-sized boulders for hundreds of miles, and it just devastated large parts of Idaho and I think Oregon as well. So there was a lot of dynamic, big scale.
So living downstream of the Hoover Dam is nothing in comparison.
Hey folks, what's happening? Welcome to Your Forest. I'm Matthew Kristoff. On this podcast, we talk about the environment and the science of sustainability. It's really just a forum for people to come on and talk about the things they love, right? So we're just a place to exchange ideas. The views expressed on here don't represent the views of the sponsors. Today's episode was really enjoyable for me. Lately, I've had this romantic idea in my head about the past and how this world has come to be the way it is. I don't mean in a political sense. I really mean we talk about paleological times, like going back in time and how did our world evolve to become how it is, from being one giant landmass like Pangea to having, 2 to 4 kilometers of ice over our heads in North America to having all kinds of craziness going on. Like, how did we get here? What happened? How did we get the boreal forest to be the way it is today? The boreal forest is the one I talk about the most on here. It's where I live. It's what I'm passionate about. It's the biggest forest in the world globally. And I just thought it would be cool to get some people on here that could talk about the geological history about the boreal forest and how it came to be the way it is. It was an awesome conversation. I'm so thankful that I was able to find a couple of people, or someone else was able to find a couple of people, if I'm being honest. Ray Darwin, thank you very much. Shout out. And to find a few people that could help me out with this quest. And the people I managed to get a hold of after a lot of deliberating and trying to find the right folks, we found 2 folks. Kendrick Brown is an adjunct professor in the University of British Columbia in Earth, Environmental, and Geographical Sciences. So he's a paleo guy. He loves looking back into, climatology, environmental change, paleo fire, reconstruction, all kinds of different stuff. And he's a perfect guy to talk to about how the boreal forest evolved to be what it is today. And the second person, also extremely important to have in this conversation, she knows more about the really far back stuff. I won't even pretend to say the right timelines because I'll just mess it up, is Tamara Fletcher. Tamara Fletcher is a paleoecologist out of the Institute of Applied Ecology, Chinese Academy of Sciences. Yeah, she's an Australian in China talking about the boreal forest. I don't know what the hell's going on in this COVID world, but it was a cool conversation. Yeah, this is a global conversation we had. Kendrick was in BC. I'm in Alberta. Tamara's in China. It was awesome. COVID's weird. I recorded in my basement. You can hear my dog barking, my daughter crying. Some realism for you in this one, for sure. It was an awesome conversation. Just really learning about the history of the boreal forest and how it came to be the way it is. However, we really wanted to bring the message home somehow about learning from our past to try to understand the future. So this whole conversation is with a focus point of climate change. And with that, we can learn about what we're doing to our own world and how we're speeding things up. And I thought it was a super cool way to look at it. Looking at all the climatic shifts that have happened over the past thousands and thousands and thousands or millions of years, if you want to go back that far, and how that compares to what's going on today. I loved it. It was great. Sponsors for this episode include Wes Fraser. Couldn't be more thankful for their support. I could not do this without them. Greenlink Forestry, same thing. Could not do this without them. Really, really crucial that they're a part of this thing. And Damaged Timber. Damaged Timber is a local company out of Edmonton, Alberta, selling damaged timber. They do a little work to it first, though. Don't worry. So they're going out into the bush in wildfire burn areas, pulling out timber from those areas and turn it into stuff you can put into your kitchen. Check them out. It's awesome. I love it. They have butcher boards and charcuterie boards and just all kinds of neat stuff that they can do. It's super, super cool. And also 10% of everything they sell goes towards a scholarship for environmental sciences, which is like, how could you not love that, right? So check them out. Your Forest 10 at checkout will get you 10% off. So, put some cool stuff in your kitchen, get some money off, put some money towards people learning more about the environment. It's a win-win-win. Go for it. Yeah. Without any further messing around, let's just dive right into this thing. Let's talk about the history of the boreal forest, how this thing came to be what it is, and yeah. Yeah, the history of the boreal forest. Like, it's not when you look up history of the boreal forest online, you end up coming down with a lot of the history of industry or the history of the boreal forest in colonial times up until now. There's not a lot out there about how it actually came to be the way it is, Mm-hmm. And so I thought it would just be a cool idea. I mean, we, as Canadians at least, I think Canadians and even globally, people, when they imagine Canada, I feel that a lot of times they're imagining mountains and forest and grizzly bears and moose and beavers and, freshwater streams and all this kind of stuff. And it really becomes a part of the identity as a Canadian, I think. And I'm sure a lot of countries feel that way about their own natural places. Right. But yeah, I just wanted to kind of dive into I don't know if you call it the evolution or what the proper word is of it, but I just wanted to dive into the idea of how the boreal forest came to be. And, yeah, so I guess before we get into it, let's get to know you guys a little bit. So if you guys don't mind just introducing yourselves quickly and just kind of giving us a quick rundown on why you got into this work and why you stayed in this work. More importantly, what drives your passion? Kendrick, you want to go ahead?
Yeah, sure. So my name's Kendrick Brown, and I'm a research scientist at Natural Resources Canada, Canadian Forest Service, and adjunct professor at UBC Okanagan campus. I guess, just a bit about my background. I have degrees in geology as well as biology, and I did a couple postdocs at the University of California and Duke University and the Department of Land, Air, and Water Resources and Department of Biology, respectively. Following that, I worked at the Geological Survey of Denmark and Greenland before joining Natural Resources Canada. And I've always been sort of gravitated to, that zone that lies between disciplines. And so paleoecology and looking at how ecosystems have changed and evolved through time, you really lie at this interface that combines biology, ecology, geology, geography, climate change. And it's a really exciting place to be because I think a lot of, discoveries going forward are going to lie at these academic ecatones, for lack of a better word. I found I was gravitated sort of to that space and really using, biological, physical, and chemical indicators to look at the evolution of landscapes and ecosystems through geological time.
That's awesome. I like that terminology. I'm sure both of you guys are very familiar with it, but the paleoecology it's nice. It's got a nice ring to it. I like it. So, Tamara, yeah, what's your background? What drives your passion? What made you want to do this, and what keeps you doing this kind of work?
Yeah, so my name's Tamara Fletcher. I'm a research fellow at the Institute of Applied Ecology at the Chinese Academy of Sciences. I started off studying zoology and then vertebrate paleontology, And during my PhD, I became really interested in what the fossils at our locality could tell us about the climate and environment that the animals I was supposed to be studying for my PhD, what kind of environment they were living in. And my interests kind of changed throughout my PhD, and I ended up writing something entirely different from what I proposed to do. So that introduced
pretty much how everybody does in academic life, eh?
That's right. So I got really interested in particularly how these amazing leaf impressions and just the diversity of organisms that were preserved at our localities could tell us so much about that environment. And so then from my PhD in kind of Cretaceous Queensland in Australia, my first postdoc was in a Pliocene climate and paleoecology in the Canadian high Arctic. So it was a pretty big change between those two, but I've become really fascinated with that environment, and I'm using the same tools but in a completely different place and answering different questions. And so
awesome.
I've stayed really, really interested in what are these processes that are happening that seem to be causing that extreme warming at the poles.
Right.
That we aren't capturing in our current climate models. So that's the overall overarching question that I'm interested in with my research.
Cool. That's awesome. So yeah, I guess I don't even know really where to start this conversation. So I hope you guys have some ideas. But I think pointing out the importance of something like the boreal forest, like I looked up just a few little stats here and there, and the boreal forest worldwide covers 1.9 billion hectares. It's 33% of the world forest area and 14% of the Earth's land base, actually. And then Canada contains, I think, 28% of the boreal forest in the world, right?
That's right. Yeah.
Yeah. Okay.
And Russia contains about 60%, and then the remainder is divided between countries like the United States, Scandinavia, Sweden, Norway, Finland, Mongolia, China, and so forth.
Gotcha.
You know, the boreal, as you pointed out, it covers a large area. It's the largest biome in the world, right? And so, you know, you can think of a biome as sort of being a large, naturally occurring community of plants and animals. And it is indeed the largest. And because it's the largest, I think people have an idea that because you have this sea of green in this high latitudinal zone that sort of circles the Earth, that it's sessile in a way, and it's anything but. It's an incredibly dynamic ecosystem, and it's a unique ecosystem. You know, one of the things about the boreal forest, certainly in Canada, is that it hasn't had profound human influence yet. You know, apart from some oil and gas exploration, hydroelectric development, forestry, and mining, but by and large, it's intact. You know, there's good examples of predator-prey interactions. There's good examples of, well, I mean, you know, there's not a lot of invasive species and these sorts of things. It stores carbon and sequesters carbon and these sorts of things. So, you know, the boreal forest is the sea of green on land masses characterized by cold-tolerant trees, but it's not, you know, it's not stationary. It evolves and it changes. And certainly, like when you look at the drivers of boreal forest dynamics, of course, you have top-down drivers like climate, but you have other drivers, fire, which is an interplay between climate and vegetation. You have insect disturbance and these sorts of things. And, you know, we all know that climate is changing now. So, you know, we've warmed, almost 1 degree in the last 150 years. Models are suggesting that the boreal forest zone is going to warm 4 to 5 degrees moving forward. So, you know, if a top-down control of the boreal forest is changing, one can expect the boreal forest to change as well.
Right.
And so the question sort of becomes, you know, how do you assess what the future of the boreal forest is going to be like? And really, there's sort of 3 general approaches to that. You can monitor the boreal forest, and in Canada, we have a program called the National Forest Inventory that has plots all across Canada, and they're They survey them every few years, and we can keep track of sort of how the boreal forest is changing in real time. Some researchers run model simulations to try and predict what the boreal forest or ecosystems or climate systems will be like in the future. But another way to sort of address the issue of boreal forest change is to look at the past. So you can go out onto the landscape and collect stratigraphic records, whether they be peat bog sections or lake sediments or fens or alluvial fans. And you can target these records that are accumulating through time and analyze them for a suite of physical, chemical, and biological indicators of ecosystem change, climate change, and sort of assess how ecosystems have changed through time. One of the advantages of the paleo approach is you can go into periods that were warmer and drier in the past and use those as first order analogs for what the future may be like. So the past sort of provides a portal to the future. And there's a whole host of other sort of advantages to the paleo approach, documenting the range of variability of systems, establishing baseline reference conditions, model calibration and validation, and these sorts of things. And so there's a lot of inherent value to understanding the past and understanding how we got to where we are today and what that means in terms of how things may change in the future.
Right, for sure. Yeah, it's an interesting thing trying to predict the future, right? It's tip of the hat to you guys for trying to sort that one out, because it's a problem. So if we were going to start somewhere to tell this story of the evolution of the boreal forest, as you guys have spent a lifetime looking into this issue, where would you start? How far back would you go?
Oh, well, that really depends on what aspects of the forest you're particularly interested in. So we know our dominant trees in the boreal forest are Pinaceae, and you could go back as far as looking at when Pinaceae split off from the other gymnosperms, and that's the breakup of Pangea, right?
Right. So pine trees, yeah.
Yeah, and then so your genera that are the main species we associate with the boreal, your pine, spruce, and larch. Your pine and spruce, we have our first fossils for those in the early Cretaceous. That's around 130 million years ago. And then larch is much more recent. We have fossils from larch in the high Arctic of Canada during the Eocene around 45 million years ago. So we have evidence for all of those in the Eocene in Arctic Canada, that around 45 million years ago. But that landscape itself isn't a boreal forest. It's more like a swamp cypress and broadleaf floodplain forest that we might associate with the modern southeastern United States. Okay. So it's a much, much warmer climate, and so you're still having a lot of those angiosperms. You've got like the hardwoods, the walnut, oak, linden, and you've got metasequoia, the dawn redwood, and swamp cypress, the Glyptostrobus, still dominant there. So as we go through, then we don't have a lot of good record of the Oligocene from northern Canada, but it seems to be warm temperate forests. So from this peak of warmth during the Eocene, your climate is cooling in a really long-term sense through to then the Miocene. That's 23 to 5.3 million years ago. You still have quite a diversity of hardwoods early in that period. You still have walnut and hickory and oak, along with spruce and pine and larch. But as you get into the middle Miocene and the late Miocene and some of these periods of cooling, because we've still got variability. So we know, looking at more recent times, we've got these glacial interglacial cycles. Well, cycles of climate cooling and warming were still happening during times like the Miocene and Pliocene, but generally at a lower amplitude, we say. So during some of these cooler periods of the mid to late Miocene, we're starting to get what we would call some of the first boreal forest up in Canada, Alaska, across, we call it Beringia. So Siberia and Alaska were still connected by a land bridge, and that whole area we call Beringia. So, and across into Siberia, we're getting your very first boreal forest around then. So from 12 million years ago.
Yeah, that's the whole. I mean, I guess for me, when I started thinking about the history, like the geological history of the boreal forest, I guess that was the kind of romantic view that I had. Right, was the idea of the Beringia, right, the land bridge between Asia and North America, and only recently, I think a few years back, I went to a museum and saw a depiction of how this, how Beringia came to be and how it went away and came to whatever, right? How it came back and forth a couple times. And then thinking about the idea of all these huge megafauna, like, the elephants and the ground sloths that are closer to, the glacial periods. And then the idea of the, 4 kilometers in some places of ice over our heads where we sit today. And so it was this romantic idea of like the amount of change that can actually happen over, like you're talking, so you were saying around the beginning of the Pleistocene, or what'd you call it, the Miocene? Sorry,
the Miocene. So
Miocene, okay.
The Miocene.
I'm not familiar, so you're gonna have to talk down to me.
Right on. The Miocenes. To put that in a little context, so our time periods from when we get our first boreal forest through to now, there's the Miocene is 23 to 5.3 million years ago. You then have the Pliocene, which is 5.3 to 2.6 million years ago. And after that is the Pleistocene, which is 2.6 to about 11,700 years ago. And then we're in the Holocene, which is our current period for about the last 12,000 years.
Right. Okay.
And just to comment on that, I mean, there's a new potential geological epoch 2, which we all heard about, known as the Anthropocene.
Right.
So humans over the last number of thousands of years have been modifying our local environments, via clearing of forests for agriculture and these sorts of things. But there's now a human signal that is becoming progressively more clearly expressed in the geological record. And so there's the potential for this new geological epoch, known as the Anthropocene.
Yeah, people love that word, hey? It gets thrown around a lot, I find, on like social media and that kind of stuff, as a type of like, oh my God, look at us, we're terrible kind of thing, right? So it's true. It is fascinating that now the major factor in what our world looks like has to do with us and what we're doing. It speaks volumes about what's going on, right?
Yeah, that's right. I mean, we won't attach any sort of connotations to human activity, whether they're good or bad. They just are. But the point is that they now are being recorded actively and well. So from a geological perspective, you have the emergence of this new epoch. And so, yeah.
Yeah, no, it is. It's fascinating. And something I want to get into a little bit later, but is also actually, you know what? We'll get into it later. I'm not going to do it now. So we're in the Miocene, right, Tamara? So we're you said 23 to 4.5 million years ago?
It's 5.3. Yep.
5.3 million years ago. Okay. So geologically, during that time, we're looking at, so you said Beringia exists at that point. So like the Asia and North America connected still? Yeah,
that's right. It's right at the end of that period that we get the loss of Beringia, I guess you could say, for the first time, and we start seeing some of the mollusks coming across that where that land bridge was and entering the Arctic Ocean. So that's how we know kind of things about the timing of when that happened. And that obviously will have changed ocean circulation and a whole lot about climate when we lose that land bridge.
Yeah, no kidding, I suppose. I never thought about that.
Mm-hmm. Good point. But so from the middle Miocene towards the end, that's when we're seeing the first boreal forests recorded with dominant conifers in a cool climate.
Okay. Yeah. And I had, I was listening to something a while back, and they were talking about, I think a lot in popular culture, we have this idea of the land bridge, Beringia, being this this place where people and animals are just like, hey, look, let's go over there. That looks interesting, and just kind of like walk over this land bridge to another spot. But we don't realize that this was a massive, huge piece of land, right? Like it was how wide was it again? I forget, but it was incredibly wide. It's not like just a bridge; it's just extra land.
Yeah, that's right. And so I mean, you have whole ecosystems that are existing on that land bridge. It's forested through this period.
Right. So there's whole species living there and dying there and everything. It's not like people use. It's not like animals were using that as just like a transportation corridor. It's like that was another part of the continent, or
that's right. Of course, during this period, it wasn't people who were wandering across.
Of course. Yeah, not yet.
but you do have interchange between the fauna on both sides, as well as it being land in its own right. Mm-hmm. So we have very connected faunas across from China and Siberia, and the faunas that we see in Arctic and in Canada and Alaska through into the Pliocene.
Right. So you said the first time we lost the Beringia was around the end of the Miocene, right? That was what you said? Yeah. Yeah. Okay. So when that happened, did we start to see any kind of? I know that the Beringia comes back a little bit later, but did we start to see any kind of divergence in the way the ecology works? Like what was happening there? Like as far as different species and that kind of thing, or is this a little too early in the game to be talking about that?
I think the divergence is happening fairly slowly over that period, but you get divergence as those two continents are separated and then go through climatic events that are maybe acting like filters or drivers of evolutionary change. So they're not necessarily diverging straight up, but you see that as those environments are put under different conditions over time.
Right. Okay. So at this point in time, how would you describe, if you were to paint a picture of what the boreal forest looked like in North America, how would you imagine it? I know you don't have they didn't have photos back then, so. But how would you describe it to people? How is it different than it is today?
I think it was still quite a diverse forest. I'm not sure if you would necessarily see a great deal of difference in terms of, I guess you'd say that the gross overview of the landscape.
Sure.
You've still got areas that are dominated by spruce and pine, or other areas that are really dominated by larch, and maybe that's a bit of a difference between the norm for boreal forest in North America today, is that there was in some areas quite a large dominance of larch rather than of spruce and pine. So it may have looked a lot more like some of that Siberian taiga that we think of today, rather than kind of the dark boreal that you might think of in North America.
Okay, but it wouldn't be alien to us. Like if we were to invent time travel today and we were to go back to this time and plop ourselves into the middle of, I don't know, whatever, northern Alberta, you may not necessarily know that you're in a different time. Like you think it's pretty familiar looking forest, more or less.
That's right. I mean, most of these, or a lot of these trees are indistinguishable from the modern tree, or some of them are indistinguishable from your modern plants. Some of them are a different species, but they're the same genera. So it's a different type of larch.
Right.
But it's very similar to the larch that we have today.
So someone that didn't know their tree species or their plant species probably wouldn't know that they've gone back in time.
That's right.
Okay, cool. That's good. Okay, I was just trying to get a general idea of how to picture this thing, right? Because I wasn't sure, like as far as like the climatic situation there, 5.4 million, 5 million years ago. I'll just say 5 million years ago.
Yeah.
What was the climatic situation like? Was it similar to today? Was it hotter, warmer, or colder, or what?
So it was definitely warmer than it is today. you almost had no tundra around 5 million years ago. Very small. It's really just coming into being as its own ecosystem, if you would, in the in kind of very mountainous or very, very high northern areas. So you've got boreal forest, almost all the way. So if you also knew where you were, it might seem quite an alien forest. Like, what are we doing in a boreal forest on what is now the Canadian Arctic archipelago? Well, at that time, it was a continuous landmass with northern Canada, and it was covered in boreal forest as well.
Gotcha. Okay, so that wasn't the species and all that kind of stuff were similar, but it wasn't exactly in the exact place that it is now, the way it's laid out now, which makes sense for sure. Okay, cool. So I guess moving forward into the Pleistocene, right? That's the next. That's after the Miocene.
So the Pliocene.
Pliocene. Okay.
That's
right. Forgive me. I'm not, like I said, I'm not familiar with this.
So the Pliocene is it's 2.6 to 5.3 million years ago, and that's been a time of really intense interest for looking at similarities to today. So with that increasing CO2, the Pliocene was the last time in geologic history that had the same or approximately the same CO2 as we do now.
Okay.
Mm-hmm.
So that, but when you say now, do you mean now with climate change, or you mean like 100 years ago, 200 years ago? CO2
now with
levels?
climate change.
With climate change. Okay.
That's right.
So like around 400 something parts per million.
Yeah.
Yeah.
Okay.
Yeah. I looked that up. We're 416 as of July 2020.
Okay. Okay.
The Pliocene, it was that pretty stable level. We have a climate that's in equilibrium with that level of CO2, which is different from today. So today, it's like we've turned up the heat on the oven, but the oven's still heating up to that temperature.
Right. Yeah. It was an interesting article I read. It was about a year ago, I think. And it was talking about when we did cross over that 400 parts per million level, there was a lot of researchers saying that this is the first time that we've crossed this 400 parts per million level in the entirety of the existence of Homo sapiens as we know them. And that last time that there was carbon dioxide at this level in the atmosphere, there was actually trees in Antarctica. Is that correct? Or is that a false statement?
In the Arctic, not in Antarctica. So we started to get ice formation in Antarctica some like 25. It was before the Miocene. It was during the Oligocene period we started getting ice in Antarctica.
Okay, so that article was wrong. I've been robbed.
Oh well.
Okay.
Don't hold
surprise,
me to that.
surprise.
I'm not studying the Antarctic, but definitely, I can tell you definitely in the Arctic we had forest.
Right, of course. Okay, so walk me through the Pliocene. What's happening to change the boreal forest during that time? What are the major factors at work?
So the boreal forest is really becoming the dominant forest on the landscape in the northern parts of both North America and in Siberia, and you start seeing much more widespread forests of that type. But it's not all boreal. So, for example, if we looked across to Siberia, to Lake Elgygytgyn, which is above the Arctic Circle, it's still at 67 degrees north. The record throughout the whole Pliocene there is still recording hardwoods, whereas at somewhere like Lost Chicken in Alaska, it's at 63 degrees north. Those hardwoods aren't there. So it's important to realize that with a lot of these sites that we're looking at, we're getting little snapshots across the landscape and in time, but there was real variability across the landscape still. Some places are boreal, some places still have these hardwoods. There's variation in climate throughout the period as well. But overall, through the Pliocene, you're going from a warm climate with boreal forest and some amazing animals living in Canada, giant camels and beaver and these kinds of things.
Giant beavers, yeah, they have. We've seen the skeletons, or not the skeletons, but the fossils of those, and they're ridiculous. Beavers the size of black bears.
But throughout the Pliocene, there's a general trend towards the cooling and that, call it climate deterioration, into the glacial cycles that later characterize the Pleistocene. So there's a lot of variability over that period.
Right. Yeah, I guess we should point out kind of, so if the CO2 levels at that time were naturally at around 400 parts per million. So yeah, that forest, because our boreal forest today, pre removal of fossil fuels from the landscape and this industrial revolution thing, we were sitting closer to 250. So we're talking about drastically different climates. Like our boreal forest today is actually not supposed to be the way it is at 400 parts per million. Like we're still adapting to what that is going to look like. It's actually more like what it looked like at 250 parts per million. Correct? That makes sense.
That's right. It started changing, but yeah, the climate hasn't come into, as we could say, hasn't come into equilibrium with the amount of carbon dioxide that we have in the atmosphere.
Yeah. Just trying to provide some context for the differences here, because I think people might get confused thinking that, it's exactly like it was today, but it's like, no, it was still very much warmer.
Yeah, very much. Yeah. And potentially 15, 20 degrees warmer in some parts of the Arctic than we see pre-industrial.
Wow, okay.
Mm-hmm.
So significantly warmer.
Yeah, so that's what we're calling that Arctic amplification of temperature. So that just means, when the planet warms, it doesn't warm evenly, and it's only going to get a little bit warmer in the tropics, but it gets a hell of a lot warmer at the poles. And so it's that effect that we're seeing that's having such a huge influence on the boreal forest during and the distribution of the boreal forest during the Pliocene. Right.
Yeah. I have to commend you for blowing right past that lost chicken name. That's an interesting, very academic name for a site. Like, what? Wait, lost chicken? You blew right past it as if it wasn't funny. It is funny. I don't know what the hell.
Well, that's the lost chicken gold mine.
Really?
Yeah.
What do you know what's behind that name? It's just the gold mine. Is that all it was? So probably some gold miner lost a chicken at some point, and that's what it's stuck with. Anyways, we're getting off track. Okay, so like that. So we're starting to get into this idea of the boreal forest as we see it today. We still have a few glacial periods to go through before we get to it, but and a few mass extinctions. But it's that idea of North America at this time. It's more or less, like, as far as the geological shape of North America, it's more or less set in stone to kind of how it is today, right? Like there isn't any massive land shifts at this point.
No, like you could recognize it on a map. And when we're talking about these different latitudes of tree line, the continent hasn't moved further north or south dramatically over that period.
Okay. Mm-hmm. But I guess I'm just trying to point out like that. Yeah, so like Canada looks more or less like Canada, with maybe some Beringia involved and a little bit of shifting of borders because of rising and dropping sea levels. I'm assuming, but it's pretty much the way it is. We're not talking a wildly volcanic situation. This is just North America.
Yeah, that's right. But the Canadian Arctic archipelago was a continuous landmass, so that looks a little bit different. It
was. Mm-hmm. I didn't know that. So it wasn't all these islands like it is today.
No, it was all connected.
Oh.
Yeah, and then as you said, sea levels were probably around 20 meters higher.
They were higher back then, and the landmass was connected still.
Mm-hmm.
So how does that work? Is that just because of ice or something, or what? What's the deal?
Well, definitely having a lot of ice sitting on top of the crust definitely weighs down the crust. So we think of land as being very static, but it's not. So you get adjustment of the level of the land if you have a lot of ice sitting on top of it. But that's not my field either.
Okay. So yeah, I was just wondering how how that worked, like why those became islands if the sea level was actually higher then than it is now.
Yeah, it's down cutting between the islands rather than sea level rise and fall.
Oh, so just the power of water pushing its way through.
That's right.
Okay, see, that makes more sense. Well, it's interesting how no matter what geological story you're trying to tell, water always wins.
It's relentless.
It is relentless, that's for sure. Eh? So, okay, so we're kind of going through the Pliocene right now. We're talking as far as, I know this is not your area either, but like as far as like megafauna are concerned and that kind of stuff, like we're not looking at humans yet. There's, like you said, there's camels and there's beavers. Do we have the elephants and like the ground sloths yet, or is that still to come?
I believe that's still to come. You've got bears and I think there's small horses living up in the Arctic region. So that's really the area that I've focused on studying. Right. And yeah, because my background's in Australia, my knowledge is quite focused on the area that I've studied while I worked in Montana. But I don't believe the giant sloths and things. I think
still
weren't in that area of Canada, at least.
Gotcha. Okay, so what, as far as the continued geological evolution of the boreal forests during the Pliocene, moving into the Pleistocene, correct? Is that right?
Yeah, that's right. So through the Pliocene, you have quite a warm early Pliocene. You get a first kind of major cold period in the late Pliocene, and then this sort of reversal back to warmth, and then you have these less regular oscillations, I suppose, in climate where you're having cooling and warming, but the trend is getting cooler and cooler and cooler to the end of the Pliocene.
Right, there was a lot of ice ages during the Pleistocene, right? Like it was up and down, up and down. It was pretty erratic time, correct?
So once you get into the Pleistocene proper, you've got huge variation in the climate, and you get those sort of glacial periods and then interglacials, but they're fairly regular in the sense that they're sort of being driven by the Milankovitch cycles, these kind of orbital and planetary cycles that are setting off changes planet-wide in the climate.
Okay.
So one of the important triggers there is the formation of the Isthmus of Panama towards the end of the Pliocene, and so that's that narrow band of land in Central America, and due to tectonic activity, which we've talked about a little bit, the isthmus, when it formed, it basically prevented oceanic exchange between the Atlantic and Pacific Ocean. And that induced, or essentially marked sort of the onset of the Gulf Stream, which started to bring warm, moisture-laden air to high latitudes, which was a trigger for Pleistocene glaciations, which, have persisted over the last about 200 or 2.5 million years. There have been about 50 glaciations or so. And we talked 50. Earlier about Homo sapiens. So Homo sapiens certainly as a genus, if not species, have been around for sort of 2 to 3 of our most recent glacial cycles.
Okay. Yeah. A lot of my reasoning for wanting to get into this subject as well was I did a podcast series called Good Fire with Amy Christensen. I'm not sure if you guys know her. She works for NRCan.
Yeah, she's a colleague.
Yeah, okay. And it was talking about the indigenous use of fire and going back, using the indigenous people of the original North America using fire as a tool to shape the landscape to their needs and that kind of stuff. And so that's a subject I wanted to get into at some point, but I'm not expecting you guys to know a lot about that. But I guess that's a little further down the line than during the Pleistocene. But I wanted to ask that question at some point, was how much of a role do you think that people played in the actual formation of the boreal forest as we see it today, right? But we'll save that. If you guys aren't ready, we can get into it a little bit later.
Yeah, we might save that for the end, just chronologically,
okay,
because it's closer to present. Yeah.
Okay, let's save it for the end. We'll get back there. It'll be a little teaser. So, continuing on with the Pleistocene. So we go through a bunch of rapid cooling and warming. I got to imagine that's got to wreak havoc on the flora and fauna of the area. Drastically changing them, right?
Yeah. So I mean, with these interglacial cycles of the Pleistocene, Tamara was talking about CO2 in the Pliocene reaching 400 plus ppm. Over the course of the Pleistocene, as we've alternated regularly semi-regularly, I should say, between glacial and interglacial periods or intervals, CO2 has sort of been remarkably stable within a band. So during glaciations, atmospheric CO2 was about 180 parts per million, and during interglacials, it would get up to 280 or 300 parts per million. And so, you have these masses of ice and these fluctuations in CO2, and you can imagine, like, these ice sheets aren't small, right? So in the last glaciation, the Wisconsin glaciation, which occurred from about 100,000 years ago to 11,700, so the start of the Holocene, all of Canada essentially was covered in ice. You had the Cadillaran ice sheet in the west covering most of British Columbia. It was maybe 2 kilometers thick, and the Laurentide ice sheet sort of covering everything east of the Rockies. And it likewise was 2 to 3 kilometers thick. And these ice sheets would form and expand, and then they would undergo ablation and they would wane. And you can imagine that, when there was ice, the vegetation, of course, isn't there. And so it's sitting somewhere south of the ice sheet, and it has to reassemble south of the ice sheet. And then when the ice starts to melt, that vegetation has to, it's responding to these changes in climate and ice conditions and these sorts of things. And it starts the long, intrepid march north, so it has to sort of disassemble itself and then move north and reassemble itself, a bit like a military family, maybe, with a lot of moves, over the course of one's career, right? We've all had friends when we were younger who had military parents, and inevitably you would hear these stories of frequent moves. Well, it's a little similar, to these oscillations in ice cover. And like I said, we've had, 40 to 50 glaciations over the last 2.5 million years. The last one sort of ending within the last, glacial maximum was somewhere between 26 and 17,000 years ago, and then the ice was sort of, gone from British Columbia, the Cadillaran ice sheet, by 12,000 years ago, and sort of the rest of Canada by about 6,000 years ago, with perhaps some remnants in northern Quebec, Baffin Island, and Ellesmere Island. But so the ice has been changing, and the plants have been continually sort of picking up and moving and then migrating in response to these profound changes in continental ice cover.
Right. So that was a question of mine. I was going to say, when you have all these glaciations happening over and over again, can plant life, or like, can the seed beds survive? Like, or are we talking, like you said, like all the plants, basically living plants, receded to below latitude of the ice sheets, and then actually had to migrate back up north? Or was there some remnant in the soil that would actually allow for, once the ice sheet's gone, they could actually just start growing, and they don't have to wait, thousands of years for them to slowly migrate via wind?
No, so the plants would be migrating. I mean, the real only hope for sort of other mechanisms would be isolated refugia, sort of microclimatic settings very close to the ice, so your migration distances were reduced. But by and large, you would see these these rather dramatic biome shifts.
Interesting.
We do see, though, that a lot of those shifts in biome happen much faster than we think. Like the scale of thousands and thousands of years for the trees to come back, sometimes they're moving much faster than that even.
Yeah, that's right. So there's been some very good DNA work, chloroplast DNA work, and of course you can have biomes sitting much further south of some of these ice sheets, but there are relic sort of disjunct populations much closer. So those migration distances can be reduced due to these sort of outlying populations of plants.
That is fascinating, though, that it's what we have in the boreal forest today is what was south of the glacial ice sheets, more or less. So that, like you said, there might have been some refugia, some patches of trees here and there that may have survived throughout, but more or less they had to, every time the ice receded, they had to come back. And so I'm sure we lost a pile of biodiversity because of that back and forth, not just because of the cold, but because of the literal loss of what was in the northern climates.
Well, I mean, when you look at so you have these oscillations in ice, each one sort of eradicates the record that the one left before it. So
right.
Sort of discerning some of the Pleistocene dynamics are a bit challenging. But I mean, if you look at just the end of the Wisconsin glaciation, right? So, when we were at maximum glacial conditions, 21 to 17,000 years ago, something like that, the boreal biome was actually, it wasn't spanning from Alaska to Newfoundland. It was located in the southeastern United States, sort of running from across South Dakota, Iowa, and Ohio down to Kansas to Kentucky kind of area, right? Okay. So it was sort of mid-southeastern United States. And, if you look at the pollen records from that time in those locations, you do see evidence for black spruce and white spruce and jack pine and fir and larch and, birch and these sorts of things. So with regards to biodiversity, the dynamics of the ecosystem would have still been in play. I mean, you would still have insects, you would still have fire and these sorts of things. You'd be maintaining landscape mosaics, to say loss of biodiversity, that's maybe not quite right. I think biodiversity would have been maintained and it would have been fluctuating as needed and in accordance with sort of environments that were available.
Okay. Isn't that fascinating to think about? It's incredible to think that the entirety of the boreal forest would have existed, in generally speaking in the, the southern latitudes, like south, like in the States and that kind of stuff. And then in the period of 17,000 years, it becomes a completely different forest down there and the boreal moves, how many thousands of kilometers north. That is incredible. Yeah.
I mean, it crosses sort of South Dakota, right? And then it enters eastern Alberta and then into northern Alberta. And then really sort of at the beginning of the Holocene when climate gets generally warmer and drier than present. So it's one of these periods, much like the Pliocene, where we look at the Pliocene as a potential analog in terms of CO2. The early Holocene from about 11,700 to 7,000 years ago, climate was, 1 to 2, some people might argue slightly more, maybe 2 to 4 degrees, certainly in the interior British Columbia, but in general, sort of 1 to 2 degrees warmer than present. So, we can hone in on that period of warmth in the early Holocene to sort of get a first order idea of what's happening with the boreal and what the future may hold. And, one of the things that happens is we have our northern tree line today, but in response to this elevated warmth, the northern tree line actually migrates, 100, 200 kilometers north of its present location, and it only retreats over sort of the last 4,000 or 5,000 years as we enter sort of what's known as a neoglacial period when climate's getting cooler and moister. One of the consequences of course, climate change might be this expansion of the boreal forest in the future, changing fire regimes, impact on wetlands and and these sorts of things. So, but
Right.
yeah, it's remarkable to think, right, that the boreal forest has sort of done this dramatic change from occupying the southeastern United States to sort of overshooting its present range to sort of coming back to where we see it today. And, our modern boreal forest and its relative position with its relative sort of composition and dynamics, it's only 4,000 or 5,000 years old. What we're seeing today, it's a relatively young ecosystem in terms of its modern configuration in space and time.
So that's an interesting point about like what Tamara was saying as well, about how fast, like our perception of how quickly the tree lines are moving. So if we were to try to put it into perspective, with today's climate change, right? So we have an increase of about 150 parts per million over the last 150 years of CO2. If the tree line was to move in accordance to that, how far north, or how far would the tree line have moved? Like, how, you know what I mean? I'm trying to contextualize it. Like, how fast could we lose the southern portion of the boreal? How fast could it end up going north? Like, in 100 years, could we have lost, a couple 100 kilometers of southern boreal forest? I'm trying to imagine because you see all these predictions, all these models of what the future forest, like where it's going to sit, right, in Canada because of climate change in 50 years, 100 years. And those are they're generally predictions of the like not the ecosystem, but the climatic levels, what the climatic levels will be at, not necessarily how fast the trees are going to move. But I was just interested in that comment that Tamara, that you made regarding the movement of trees and how fast they can actually move. Because my perception was that it took a couple thousand years or something to do that. But I just wanted you to expand on that thought.
Yeah, we can also see, like, climatically and ecologically, you can see, climatic and ecological states and trends, right? And so a trend is sort of a long-term gradual change. And certainly in Western Canada, we see some of those over the last 5,000-6,000 years. But prior to that, you see these state changes where an ecosystem over just a few hundred years can very quickly alter sort of its composition, structure, and character, as species arrive and expand either through sort of intra-specific species competition. And,
Gotcha.
And so we're at this point here with greenhouse gas emissions and whatnot that I would hedge that we'll see a relatively rapid reorganization. We're not going to see sort of one of these millennial scale trends of change, but rather one of these much more abrupt state changes.
Yeah,
so it's hard to predict, is what you're saying.
Well, one of the things you're seeing state changes in the forest itself, but we also have these stepwise rather than necessarily gradual changes in the climate. So far our modern climate models are predicting that amplification of temperature that we've seen so far in the Arctic with the amount of CO2 we've already got in the atmosphere. But if we look back at the Pliocene, those same models can't get the kind of warmth that we can estimate from the flora that was there. And it seems like there's these long-term feedback mechanisms that aren't invoked in our climate models that were having an effect on the climate that was in equilibrium with the levels of CO2 we have now. So we may find that we get to a particular point, and then there's a stepwise or a state change in the climate as well. And so knowing exactly when that will happen or whether that's going to happen, there's potential that the changes that we have had in terms of global geology and different cycles in the ocean and even the amount of aerosols that we've put out into the atmosphere, we could end up with a very different endpoint from the Pliocene.
Right. Okay.
And it's not only sort of migration of species, but the controls of the boreal forest are climate, but they're also biological processes or biochemical processes, whether it be fire, insect disturbance, or disease. And so, as fire regimes change in response to changes in climate, any change, let's say, in fire severity moving forward can also have a profound impact on the new emergent composition of the forest. And so if we start seeing, much higher severity fires, right, that actually might be favorable for deciduous species to emerge. And so you might actually see a greater, compositional representation of birch in the boreal forest if fire severity changes. So you start getting into all these very complicated feedbacks and mechanisms, and there's many of them, and we all sort of work in our silos and do our best to interface and whatnot, but the system gets complicated pretty quickly.
There's a lot of research going on, and it's hard for everybody to talk to everybody all the time. So, before we continue on, I wanted to kind of the whole idea of of the glaciers, right? And these massive, what did you call the last glacial period, Kendrick?
The Wisconsin glaciation?
The Wisconsin glaciation. Okay. So that ended, you said, roughly about 12,000 years ago?
Well, I mean, you have full glacial conditions from sort of 26 to 17,000. So that's when you have this massive ice sheet covering much of Canada and the northern United States. From sort of 17 to 12,000, the ice is retreating. It's melting. So there's changes in what are known as Milankovitch cycles. So these are changes in orbital geometries that influence the amount of insulation that's reaching the Earth's surface that sort of drive some of the climate change that we're seeing. And so the ice starts to melt in response to these. By 12,000 years ago, Western Canada is ice-free west of the Rockies. East of the Rockies, the Laurentide ice sheet is still melting, and it sort of becomes centered around Hudson's Bay. And it sort
it's
of
a ridiculous sized piece of ice. Like, I mean, to go across, 3,000 kilometers of, distance just one way is like, I can't even imagine, like, just the proportions of a piece of ice 2,000 meters thick, so 2 kilometers high.
Yeah, no, it
doesn't make sense.
No, get this. When I was an undergrad at Dalhousie University in Nova Scotia, I did my thesis using marine protists known as foraminifera, and they're very sensitive to changes in salinity. And so we cored a number of sites in a tidal marsh, and we used the foraminifera to reconstruct sea level. And so under full glacial conditions, with all of this ice on the land, the sort of eustatic sea level was 100 meters lower than today. So Tamara talked about Pliocene sea level being 25 meters higher. Under full glacial conditions during the Wisconsin and presumably earlier ones, sea level was much lower than today because all that water was tied up in the continental ice. And so, you're seeing these massive fluctuations. So sort of just to put this in context, when you're thinking and trying to visualize this massive ice over North America, global sea levels were much lower than they were today.
So I'm going to need a refresher. I just realized that I take for granted the fact that there was a bunch of glacial periods. I just realized that I don't remember how the hell we managed to get 2 kilometers of ice above our heads for a few tens of thousands of years. How does that? What is the mechanism there? Like how? Like I understand the cooling. The Earth is cooling, but
yeah.
So how does that water get there?
Well, I alluded to it earlier. It all sort of starts with the closure of the formation of the Isthmus of Panama. And what happened there was warm tropical water. So the Gulf Stream sort of got intensified at that point because you didn't have exchange of water between the Atlantic and the Pacific. So the water in the Atlantic got redirected north. And so you had the intensification of the Gulf Stream, and that brought warm water.
What do you mean by intensification? Sorry.
Well, it's just like before that water could exchange equatorially between the Pacific and the Atlantic Oceans. When Central America formed, that water that was exchanging got redirected north, and that's kind of what I mean by the intensification. So you start seeing the formation of the Gulf Stream, and what that did is it brought warm water to high latitudes, but it also brought warm, moist air to high latitudes. And when that warm, moist air got to higher latitudes, it cooled. And it rained out in the form of snow, and you start seeing the accumulation of snow at high latitudes. And so you have this sort of oceanic dynamic that starts to interplay with these Milankovitch cycles that Tamara mentioned earlier. And with that interaction, you start seeing ice sheets forming and contracting and forming and contracting.
Could you imagine the forecast on that? Be like, oh yeah, over the next 12,000 years, we can expect about 2 kilometers of snow, and ice formation above our heads. And then like, it's amazing the forces at work on the global scale. Hey, like I think as humans, we tend to forget the powers that be there, the work what's being done. Like I can't imagine it would snow so much that it would turn into ice that's 2 kilometers thick. And then moving on from that, talking about, the receding of that ice, like the grinding out of the landscape because of that ice going back. Like, it's not like you put an ice cube on a tray and it just kind of melts away and goes into the water. Like we're talking about, like, as these things receded, they literally were pieces of ice that they were kind of moving across the landscape, correct? Like, so gouging out big areas of land and all kinds of stuff like that, right?
Yeah, that's right. I mean, you see glacial grooves and striations all over exposed bedrock. A lot of the lakes that you see sort of dotting across the boreal biome owe their history to, sort of remnant ice deposits that melted later and sort of left this cavity in the landscape that filled with water. And I mean, some of these lakes could get dramatically huge. So there was one lake Agassiz that it was sort of at the edge of the ice sheet about 12,000 years ago. And Lake Winnipeg's a remnant of this, but, Lake Agassiz essentially covered all of Manitoba, right? And big enough that when it drained, it altered the global climate system for about 1,000 years during an event known as the Younger Dryas, which was a cooling event.
Fascinating example of this was the glacial Lake Missoula. So I got to live in Missoula for a couple of years, but there was an ice dam there that was over 2,000 feet tall, something huge. And when that dam burst, you had massive floodwaters that moved, car-sized boulders for hundreds of miles, and it just devastated large parts of kind of Idaho and I think Oregon as well. So there was a lot of dynamic, big scale.
So living downstream of the Hoover Dam is nothing in comparison.
Yeah, well, it is amazing to look. Like I do forest inventory, and so looking at a lot of images all the time of the forest, and you can see, I never noticed it before until I had a geologist in the office and was kind of showing me around at some of the grayscale LiDAR stuff that we have and showing me the remnants of glacial recession, right? And I was like, oh, okay. So like now I'm starting to see it everywhere, of these remnants of the last glacial period in the landscape, right? It's a crazy force to have that. Like, how much does that weigh? I have no idea. Like, you take half the ocean and put it on the land. Oh, it's something else.
Yeah, I mean, it's, the ecological and geomorphic and geological processes. I mean, they are wonders of the earth, right? And we're talking about it here, and you see these things, but I'm from Nova Scotia, and you drive out to a place called Peggy's Cove, and, it's this granitic landscape that's just dotted with boulders, the size of cars. And I mean, there's literally thousands of them, right? And you wonder how they get there. And of course, it's ice processes that were doing it.
That's so cool. I love the thought of that. Oh, okay. We went on a little romantic little spill there about glaciers. If we've gone back onto the forest here. So right around this time, right around the last glacial period, we think around 15,000 years ago, I think, is when we started to have the first kind of humans moving into North America, as far as I remember. Is that correct? You guys think?
Yeah. So as the ice was melting, I was talking about the Cadillaran and the Laurentide ice sheet, and they were sort of juxtaposed until about 14,000 years ago. And then a corridor opened up between them, known as the ice-free corridor. It would have been characterized by herb tundra in the north and probably shrub tundra in the south. And that was one of the mechanisms, the original sort of proposed mechanisms by which, the early peopling of the Americas may have taken place. Since then, as I'm sure you and many of your listeners are aware, there's been a coastal route that's also been put forth as a potential pathway for sort of the early peopling of the Americas. But yeah, so sort of around 15,000 years ago, the ice-free corridor was there. I do believe wasn't there just a story in Mexico last week where they actually found some human-related artifacts in a cave that were actually dated at 30,000, so much, much older. So people may have been in North and South and Central America much earlier than previously thought.
Okay, and do they think that those people came across Beringia as well, or what are the theories there? Do you guys know? Just briefly. I know it's not your area.
Oh, I just heard the news cycle, so I don't know the specifics of that study. Right. 30,000 years ago, you're into sort of full glacial conditions, so you would have a Beringian landscape. The ice would, how you go from there, hard whether it's coastal route or some overland route, who knows? Yeah.
Yeah, because I remember hearing some kind of, there was a couple of theories that it may have been, the folks that colonized like Hawaii and that kind of stuff. What's the terminology for them? I'm having a brain fart here.
Polynesians?
The Polynesians. There was some theories that people thought that maybe the Polynesians or their ancestors may have colonized South America and that kind of stuff. But that's not my area of expertise, and nor do I think is it yours.
No, but there are some old sort of dates associated with potentially sort of human-occupied sites down there. So yeah, it's
30,000 years is cool.
If life was
that's
longer
cool.
And we had more time, it would be interesting to engage in some of these other disciplines.
Yeah, no kidding, right? So do you know of around this time, around 14,000 years, when we start to see evidence of humans moving into North America, is there any kind of evidence of their role in the landscape as being one that starts to form the landscape? Like we talk about being in the Anthropocene now, but like I was saying earlier, right, there's some argument amongst like First Nations people that they've been doing landscape management for since time immemorial. They say that they've been harnessing fire and using it as a tool for landscape management since they got here, according to them. And so I wanted to know if there's any evidence of that in the fossil record or however you guys do it, right? Like, is there evidence of humans being landscape managers or something like?
Yeah. So, just a couple things here, at about the time that we're talking sort of the 13,000 year range, one of you mentioned earlier about sort of Pleistocene extinction. So this is when a lot of large mammals went extinct, bison, oxen, camels, species of bison, oxen, camels, horses. We had lions in North America. We had jaguars, the saber-toothed cat, woolly mammoths, mastodons. And, there has been...
My favorite's still the giant ground sloth. That thing.
Yeah, the ground sloth and the giant cave-faced bear and the giant beaver and these sorts of things. And so there is a considerable amount of debate amongst people that work in that discipline, what the drivers of those extinctions were, whether they were climate or human or a combination of both. So there's one potential example there of sort of, humans perhaps modifying, fauna, which would have, of course, had consequences for ecosystems. One of the things I work on is looking at sort of late Pleistocene, Holocene fire records and examining how fire regimes change through time. And one of the challenges that we have is, of course, there's natural fires ignited by lightning, but there's also a human presence on the landscape. And certainly, from sort of a coastal British Columbia perspective, so not the boreal, but on the coast here, we've seen evidence that I've certainly interpreted as sort of human burning, as far back as 7,000, 8,000 years ago. In the sort of later Holocene, we do, in some of our records, see, let's say like 2, 3, 4,000 years ago, profound increases in charcoal at some sites, not all sites. But at the same time, you have an increase in climate variability occurring at about that time as well. And so it's very difficult to sort of parcel out, what's related to climate variability and what's related to humans. But undoubtedly, right. Of course, people have been here for a long time. We have artifacts. People were burning. From the boreal context, Aboriginal First Nations peoples would have undoubtedly been using the boreal forest. They occupied it for thousands of years. They would have been using the wood for shelter, building canoes, traps, fuel, maybe some tools even. They would have been hunting ungulates and eating fish and maybe bear and these sorts of things, the hides for clothing. And I think, undoubtedly we could all make the argument that, more recently sort of with the European colonization of North America, of course, that those numbers declined and people were no longer sort of burning land and maintaining landscape mosaics, and we lost that element on the landscape. But surprisingly, Matthew, there are a number of cores across the Canadian boreal forest, but the number of sort of sedimentary records that have been examined for pollen and charcoal, you're still sort of numbering in the dozens. I mean, it's not hundreds or anything. And we really need to increase the number of records to sort of drill into the question you're asking and
Sure.
come up with some sort of scientifically defendable conclusions. There's tantalizing bits and pieces that you see, but really more work needs to be done. But undoubtedly, we've been here for thousands of years, and they've been living in and utilizing the environment.
Right. It was a question I think based out of I made a point that there in a previous podcast that perhaps it might be arguable to say that the boreal forest as we see it today, or up until even pre-colonial times, it could be argued that forest would not have existed the way it was without the existence of human beings, and that human beings were a part of the evolution of this forest, right? It was kind of an interesting take, because I think it's one of those things where people often look at, wilderness, quote unquote wilderness, or pristine wilderness and that kind of stuff, right? And they go, untouched by humans. But the reality is they've been there for thousands and thousands of years, and they've been potentially, they could have been changing the landscape during that time and part of the ecology of it, right? It kind of changes our viewpoint of our role on the planet if we start to see ourselves as part of the ecology instead of kind of ruler over the ecology,
Yeah. I mean, the boreal is an immense place, as you alluded to. What did we say there at the beginning? 2 billion hectares globally of boreal. So there's a lot of land, and population densities would have been relatively low at the beginning, increasing through time. So through time you'd have more evidence of sort of human modification of localized landscapes for sure. But right. All of the human activity on the landscape, it's superimposed on a climatic ecological sort of backdrop, and so like there's many sort of disparities in a way in the record. Like if you look at the fire records from Alaska just over the last number of thousands of years, the charcoal records tell us that the amount of biomass burning in Alaska has increased through time, partially regulated by sort of the arrival and expansion of black spruce, which is flammable, resins, lichen, and these sorts of things. So we see sort of biomass burning increasing in Alaska, whereas in Northwest Territories, northern Alberta, Manitoba, Saskatchewan, we actually see fire decreasing over the same time period. So in sort of central Western Canada, we see a peak in fire activity in the early Holocene when climate was warmer and drier. And then our fire regime seems to sort of, the charcoal records anyway, the concentration of charcoal, they decrease through time commensurate with changes in climate when climate starts getting cooler and wetter. And so, you have these two sites, sort of Alaska and central Canada, juxtaposed to one another with opposite trends in fire dynamics based on, dozens of charcoal records. And then superimposed on that, of course, is human activity. So again, it gets complicated quickly, and trying to decipher these records can be a challenge sometimes.
Yeah. It's almost like science needs more funding.
Go figure. Hey, Tamara.
So would you guys say that, after the Holocene is, when's the Holocene again?
The last 11,700 years.
The last, okay, gotcha.
11,700 to present day.
Okay, so would you say the Holocene, you could basically say that is, obviously there'll be shifts and there'll be changes in the boreal forest over time throughout that period. It's a big chunk of time, but that is pretty much the forest of today, more or less.
Well, in the early Holocene, it was migrating, right? So at the beginning of the Holocene, the boreal forest was sort of reaching eastern Alberta, but it was moving north.
What about the Great Migration? Yeah.
the Great Migration. So, but the modern boreal forest, when you look at a map of the boreal forest today and the distribution of it, if you sort of looked at a map from, let's say one of these early people there, sort of had the luxury of having a stratospheric sort of view of the boreal, 6,000 years ago versus today, the distribution map of the boreal would look very similar.
Gotcha. So around 6,000 years ago. That is a very short period of time, realistically, right?
Yeah.
It's a sliver.
Yeah, if you think of a human generation, and you guys can help me with the math here, but if you think of a human generation, let's say being 20 years, so you have 50 generations per 1,000 years times 6. It's your great times 300 grandparents ago.
Right.
Right, which is sort of the emergence of the modern boreal in terms of its spatial distribution.
Yeah. Yeah, it's not that long ago. Like I think as human beings, we have this weird concept of time, right? We're only around for a little short while, but on the geological time scale, it's just a sliver. So it makes you wonder where we're headed, right? What's the future? What is it going to look like? Especially with, human caused climate change and the speed at which human caused climate change is changing climate, right? So, before we move on to that, kind of I want to get your guys' predictions of the future, but is there any interesting kind of factoids, anything that you wanted to point out about this whole process, this whole, geological evolution of the boreal forest, anything that you didn't get to say that you wanted to throw in there?
Well, I was covering only the last 2.5 million years. Tamara, I think, had the previous 27 million or something. I don't know, Tamara, have you missed anything?
I'm sure I've missed so many things, but I think kind of a takeaway.
Timeline.
Kind of a takeaway is just that it's massive variation both over time, but even over space within the same time period. So we talked about, if you went back 5,000 or 6,000 years, the distribution, where the boreal forest is might look pretty similar to today. But if you look across that boreal forest today, you're still going to see massive massive variation. And so you've got huge variation, between here and Siberia. We might still, a lot of people use taiga and boreal interchangeably, but those are massively different ecosystems, particularly in things like fire, that we're really interested in knowing how that's going to change. So those interactions between the kind of species that are dominant and the climate and the soils and then the geological history of a location, there's so much variability within the boreal. It isn't just kind of one ecosystem, I think.
For sure.
And I think I'll just add to sort of the spatial and temporal. I'll maybe do a plug for the type of research that Tamara and I do, and that is, how do we even know about climate change? We know about it because, we have these
sounds like a question
term...
somebody that's really high would ask, just so you know.
Yeah. One of the ways we know about it, of course, is anecdotally. We all have seen changes over the course of our lifetime. But, we have sort of these decadal records, like the Mauna Loa CO2 record, which is showing CO2 increasing through time. But that in unto itself, if you just look at that 50, 60 year time series and you see an increasing trend, you recognize that CO2 is changing, but but it doesn't provide a lot of context for that. So,
Sure.
To get more context, you want to look sort of at a longer time series. And so Michael Mann developed, the very famous hockey stick curve of temperature change over the last 1 to 2,000 years. And what he shows over that time is climate is, relatively stable, sort of generally or slightly cooling through time. But then just within the last 150, 200 years, it shoots up, right? And so now you start gaining some more sort of perspective on like the degree of climate change that's happening. And then you sort of turn your attention to these longer time series, the Greenlandic and Antarctic ice cores, where they're looking at, measuring CO2 trapped in bubbles in the ice. And, they capture 1 million years of atmospheric CO2 oscillation. Where I said earlier that CO2 between glaciations and interglacial. So when we were covered in ice to covered in a sea of boreal forest, right? That the CO2 was sort of ranging between 180 and 280 parts per million. Well, in almost instantaneous time, we've shot up to 416. And so, the paleo work that we do, it provides incredibly valuable context for climate change. And, again, there's lots of applications, whether it's first order analogs, calibrating and validating models, assessing sort of the ranges of variability, all of these different things you can sort of, extract out of paleo records. And, we're more and more trying to integrate and use paleo ecology to help inform sort of smart management decisions as well.
Right. Do you guys ever, as people who dedicated their lives to looking into the past and looking at change over time, do you guys ever look at humanity and think, oh, how silly you are to try and hold on to what you have? Like it must be weird for you guys to look at us and like the idea, even I try to think about the idea of conservation, like land conservation, and then we put it into the context of something like this, like change over time. You go, okay, but how are you going to fight against the world, right? Like it's like the actual planet itself. It must be a weird thing to try to balance your guys' perspective of such a long time scale and then to try to contextualize that change in our current living situation.
I think one of the things that really long time scale perspective has given me is an appreciation of just how rapidly we're changing the environment that we're living in, though. The rate at which we're releasing CO2 into the atmosphere is incredibly fast, even compared to some of these, what we would call, spikes in CO2 of the past, times like the Paleocene, Eocene climate optimum. These times that had massive dramatic effects in the fossil record, and we're exceeding them. And I think that makes me, in some ways, very, very concerned for conservation, because how can we manage something that's so unprecedented? So I think we're having we're having maybe an even bigger impact than that natural variation that we've seen in the past, at least in kind of the more recent geologic past. I think that's something to be very wary of when people say, "Oh, well, there's been climate variation in the past, so we don't need to." Be so worried about it or whatever. It's like, no, we should be really worried.
Yeah.
Yeah. And not only that, I'll just add, because I think that's a very important point there that Tamara made. But, I guess from my perspective, I talked at the beginning of the program about how I really enjoy sort of being in the saddle at the interface between multiple disciplines. And so, and Tamara and I have worked on some projects together, and, we talk about fire, we talk about forest composition, we talk about beavers, we talk about lateral channel migration. And so when you do paleo work, you collect cores or analyze sequences, but more often than not, you're not just focusing on a biological or ecological element. There's a lake level fluctuation, there's stream flow dynamics, there's glaciers, there's, and so you get sort of into this, again, this interdisciplinary zone. And I guess the only thing I would like to say is that, as the consequences of climate change manifest themselves, like nature and landscapes don't exist in silos. Everything is interconnected. And so when the system starts to change, it's not just going to be an ecotonal migration of, 100 meters. The ecology is going to change. The geomorphology is going to change. We're going to feel the impacts of climate change in our rivers, in our lakes, in our forests, in our oceans. And so it's going to be a complete integrated response. And we often see those types of integrated responses, whether, we work with upland indicators or aquatic indicators. They often all are responding to intervals of climate change in the fossil record, and you see that. And so, an important message is that, when it all goes together, right? Whatever direction and whatever the ultimate consequences are, it's not just a single system in isolation.
For sure.
And so managers need to plan, not just for changes in sort of forests and whatnot, but indeed the entire landscape.
Yeah, for sure. It's interesting that for you guys, with the perspective you have, that you haven't managed to get this, oh, whatever, what does it matter attitude. You actually have a more engaged attitude towards, the impacts we're having, because you recognize the context of it all, I guess, a little bit better than everybody else, right? I don't know if I want to even ask you guys to try to predict what you think the changes are going to be in the boreal forest, or, globally even, with climate change. But I think I'm going to ask you anyways. If you guys had to make a prediction about just general trends, however detailed or undetailed you want to go, just quickly in a minute or two, what do you think are some things we can expect to have happen over the next 100, 200, 300 years, whatever timescale you want to go with?
Tamara, do you want to lead or do you want me to go?
Oh, you can go first.
Okay. It'll be sort of a 10,000 foot sort of overview.
Sure.
But, we have a lot of permafrost in the boreal forest, and of course permafrost is going to be melting. We're going to be releasing methane from that. And so, there's the potential for accelerated greenhouse gas emissions. But we'll see permafrost melt. We're going to see an alteration of forest fire regimes, increased burn area, severity, frequency, ecotonal boundary shifts. Maybe, new ecological trajectories as fire severity patterns change. Wetlands, which we really haven't talked about, but the boreal forest is dotted with lakes and wetlands, whether they're bogs or fens and these sorts of things. Ecologically diverse systems, especially in the West, if we experience more droughty type conditions, some of our wetlands will potentially be at risk for drying out and these sorts of things. Although I do think the boreal forest overall has gotten a little drier, wetter through time, but we're also certainly in the West at risk of sort of prolonged periods of drought. And so, I think we're going to be seeing all of these types of changes. They have the potential to be cumulative and interact with one another, and we're going to have to do our best to manage our forests for not only their sort of ecological and functional value, but also for the people that live and make a living with the boreals. So it's going to be a challenging time. And again, sort of getting back to this idea of an integrated system, you're going to have to do this while you're managing, sea level rise, crop failure and desertification elsewhere, ocean acidification, and all of these things. So, the environmental, what's the word I want to say here? Sort of the environmental challenges, let's say, are daunting, but Homo sapiens as a species, we have big brains and hopefully capacity to recognize these issues and follow the science and do our best to sort of mediate things. But change is coming and we need to be prepared. And again, just putting a plug in sort of for the paleo, I think the best preparation we can have is a combined approach of monitoring our systems, simulating future conditions, and looking at the past. And when you have all of those different spatial and temporal perspectives, you've armed yourselves with the best knowledge to make logical, science-based management decisions.
Awesome. That's good. Anything to add, Tamara, or are you just going to let him have the last word?
I think it's, as Kendrick was saying, it's really important that we be informed, and have hope as well. Sometimes it can be hard to have hope about the future of our climate, even more so, I think, when you work in the paleo record, because I think our paleo record is suggesting there's going to be kind of even more dramatic change than our current climate models are maybe suggesting. But yeah, we're an ingenious species, and I hope that it becomes more and more tangible just how big an effect we're having, that all of us do our bit to mitigate those changes and to think about the impact that we are having on our planet. So I think there's a sort of saying that humans we overestimate what we can get done in a day and underestimate what we can do over the long term. And I think we as people underestimate what we can do long term to change our impact on the planet. And I hope that we're going to do that, and that our awareness of the problem is only increasing, and that it's something that we can solve, but big change is coming.
And certainly in Canada, you'll often hear, we're a small contributor to the overall big problem. But the reality is this solution, just like paleoecology, where we look at things from different spatial and temporal scales, the solution also is going to come from different scales. So it's going to come at the individual scale. It's going to come from the municipal scale and the decisions that people make at that level, at the provincial scale, at the national scale, and then through international cooperation.
Absolutely. No, we should take up however much of the responsibility we can, in my opinion, for sure. Right?
No,
If
that's
we have
right.
the power
Everyone has to
so.
do their bit and more. Yeah.
Absolutely. No, I totally agree. Well, that was awesome, guys. Thank you so much for taking the time to try and break this down, especially in the context of, our current climatic situation. It's a big task, but I think you guys managed it pretty well. Congratulations.
Oh,
you did
it's
it.
our pleasure. Yeah. Thank you.
Yeah, thank you for having us on.
Thanks a lot for listening, guys. I hope you enjoyed that. If you have any questions, anything you want to ask me or any of the guests, send me an email, yourforestpodcast@gmail.com, and I will definitely get back to you. Please rate and review, share this podcast. Anything helps. I really appreciate it. Take it easy, guys. We'll see you next time.